everyone. Welcome to the session. This session, we will have Ivana Milovanovic and myself, Mengyuan Liu. We are both data scientists at SAP Concur. We're going to talk about the tips and tricks we learned for developing deep learning image models for mobile production. Just a quick note that to post your questions in the Q&A tab instead of the chat. And then we'll get started. Off you go, Ivana.
Hello everyone from me as well. Nice to see you all. And yeah, as Mengyuan said, we'll be sharing a few tips and tricks that we learned from our everyday work. So let's get to it. So Mengyuan and I are both data scientists working on this specific product called Expensive. And we're quickly going to show a demo of the product. Ready? Oh, just 1 second.
This is the Concur. This is the Concur mobile app. In the app, the user can take a photo of the receipt, and the on-device model will extract the total amount on the receipt for the user to confirm. It fully supports the handwritten amount. Then the receipt is sent to the backend for further analysis to extract other key information such as date, currency, expense type, location, and vendor. Then these automatically extracted tokens are returned to the user to automatically create an expense in their expense report without manually typing in all these values themselves. After capturing all the expenses, the user can submit the report for approval for reimbursement.
Okay, so as you may have seen in the demo, we work with our customers' receipt images, and then we have some algorithms that are returning tokens earlier than others. The reason for that is that they work directly off of image to return the tokens. So one of those that you've seen in the demo is the algorithm that returns the total amount of a receipt. And I will just quickly go over this model. So we start from this receipt image, and then we give it as an input into a convolutional neural network, where we use this to extract valuable features. And then from here, we put this into an encoder-decoder model with attention that allows us to extract, to find and extract the amount character by character. We have another algorithm that's working directly off of images, and that is our language detection algorithm. This one is used to provide a language hint to optical character recognition engines. And we again start from a receipt image. We put it into a convolutional neural network, where at 3 different depths of this network, we take outputs and concatenate into a feature vector. From there, we build a classifier that is able to classify this receipt into one of these language categories. So not just that we have these image-based models, but the experience was enhanced by having the models on device. Why? Because these models that way are faster. There's no need to upload the entire image to the cloud, and there's no round trip to the backend server. These models can be privacy preserving if they're working just on device, and they're not dependent on internet connection in general. However, when working with ML on edge devices, there are certain constraints, and those are related to limited resources on your device, like memory and disk and power of your mobile device. And then at SAP, at least, we have so many customers with many different phones. They have different hardware ecosystems. So it's really important to cover all those. And then from these constraints, there are certain requirements that arise, which are you need to have a lightweight model, so meaning small, and then also the model that predicts really fast. So you need a low latency output. So the content of our talk will be quickly going through how we prepare images for training, what we do to make our training faster and mobile friendly. And lastly, we'll talk a little bit about deployment, the quantization that we're doing to make the model faster and smaller, and then how we eventually benchmark our ML models on the variety of mobile devices. So image preparation, as with any computer vision algorithm, you would go from the original receipt image, and then you would resize and convert it to a grayscale. And from there, you would apply a bunch of augmentations, such as cropping, rotating, shearing, to make your training algorithm more robust to all these different inputs and variations that it might be seeing in production. So let's go and switch to training. Here, we won't really be able to show our own code, but we'll be showing this hello world example of computer vision called MNIST, where we are dealing with handwritten digits data set. And luckily, this one can be modeled with a pretty simple model of having a convolutional network to extract features, and then having dense layers that do the classification of each image into one of the 10 digits. So just a reminder that TensorFlow is a framework that we'll be mostly talking about, although the concepts here are more general. And the TensorFlow is a framework that we work every day in. But ML algorithms in TensorFlow are represented as computational graphs. What does it mean? It means that even though you might be writing your code like something like here, where you would have each line executed line by line and having the results be sent to you immediately, that is not really how TensorFlow works. So in the background, it operates as a graph, more like something shown to you on the right, where different operations can be parallelized, and these graphs can be optimized in all these different ways to make your ML models run faster. So what does it mean for you? If you're training and inferencing using built-in APIs, and you can recognize these like model fit function, for example, you don't really need to worry about this much. Because you would, the way you would train an MNIST model, it would be to define a model, to specify here a loss function, optimizer, a metric. And then once you do a model.fit, TensorFlow will actually execute your code as a graph by default. So you would notice that the step execution is pretty fast, and it's 9 milliseconds per step. However, in our everyday work, you may want to have more control over your training process. We need to customize oftentimes a lot of things, including we have models that are with multiple inputs and outputs. We need to customize the loss function, or maybe we just want to access gradients and update them in a certain specific manner. So in that case, you would build a custom training loop. With MNIST, it will look like something like this, where you would have iterations over epochs, and then within each epoch, you would iterate over your training set. And then you would make this train step function, where in each pass, you would do a forward pass through the model to get the predictions back. And then based on labels, you will calculate loss and update your nets weights. However, if you were to write a custom loop like this, you would notice that it's actually running much slower. It is now 14.6 milliseconds for this simple example. And the reason for it running slower is that it's executing eagerly, so it's not being compiled as a graph. The way to compile it as a graph is to decorate with tf.function. This decorator will signal the TensorFlow to compile into a graph whatever code is underneath, including the function that this function is calling. So with this, you will get 7.7 milliseconds per step, which means that now your training is 2 times faster. And you can do the same decoration of your inference loop as well. And just to get back to our own models, we've seen the benefits of using this in our everyday work. Specifically for amount detection, we've seen the improvements in training where we're training in batches of 20 images, which is now 30% faster. And again, inference on a single image was 50% faster after we use a custom loop with tf.function. There are certain tips and tricks around using this that you need to be aware of. For example, once you decorate with tf.function, all your code will be transitioned into a graph mode, and you won't be able to debug it with a debugger. So do your early development and debugging without tf.function and decorate once ready. Another tip would be to make sure that your output of your model is the same in both eager and graph mode. So just make sure you're getting the same outputs. And then also avoid using certain things in your training step loop. So avoid using Python lists and iterators that are changing. You can think of a graph as a snapshot in time. So whatever, if you have something that's, for example, appending to a list, like shown here, and you decorate that with tf.function, that can lead to very unexpected behavior. So just make sure to double check everything. And now I will just give this back to Mengyuan. She will be telling you a bit about mobile-friendly training.
Thanks, Ivana. Now we see how to make the training faster. Let's see how to make it mobile friendly as well. First, I want to introduce a concept of quantization. It simply means to quantize all the weights from 32-bit floats to an 8-bit int. It works because the deep neural networks we know are very robust to small changes, so such as rounding of the weights. So that wouldn't help affect too much on its prediction power. And also, we know that the weights and activations within each layer usually lie in a smart range. So what quantization really does is to map all these floats in a small range to an 8-bit int. How it works is you will train the model in full precision and then quantize the weights to a fixed point. TensorFlow provides a simple API to do this, and we will cover that later. However, sometimes it might be too much loss in accuracy depending on your requirement for models with less redundant weights. So in these cases, what we can do is something called quantization-aware training. So what it really does is that during the training, you will try to mimic the quantization loss during training by adding this fake quant nodes. Essentially, all these nodes, what they do is during the forward pass, it will try to convert the 32-bit float into an 8-bit int, and then convert it back to the float format with the quantization error within it. So in this case, all the weights will be still in the float 32 format, though it can be converted directly to int without any loss in accuracy. And during the back propagation, you still having this float weights that you can use to calculate the accurate gradient updates. TensorFlow provides the easy API to do this. You can use it with the functional API. All you need to do is use the tf function and to convert your model to a quantization-aware model and then train that model. Another way that we can have smaller memory and storage footprint on devices is trying to share architectures between models if you wanted to put multiple models on the device. Going back to our example of MNIST, let's just say we want to have two predictions. One is what digit it is. We also want to predict if it's an odd and even number. If we put these two as two separate models on device, then it will take up twice as much as the storage and memory. So what we can do is trying to have these models share some part of architecture, if not all. So in this example, we can clearly use all the same convolutional layers for both outputs, while just setting two different dense layers, one specifically for each output. We can also set up the loss specifically for each output and train this multi-output model as one. Of course, there are ways to custom the loss when you're trying to combine these two outputs into one model. In the lab, you can easily just use a simple sum of the two losses as your total loss, and then you will train the model equally. However, in some cases, we might care the accuracy about one specific model more than the other. In this case, we can use this kind of weighted addition for the custom loss, and you would put more weights on the output that you care more about is accuracy. In this case, it's digit prediction. Now, coming back to our work of having the language and amount detection on mobile, what we are trying to do right now is to have the two models sharing the same CNN part, and then after the CNN, a separate RN with attention will help us with the amount detection, while just a simple fully connected layer will help with the language classification. Now you have your trained model. Let's see how we can deploy it. Regardless whether you did the quantization-aware training, as we talked about before, now it's the time for you to do some post-training quantization. TensorFlow Lite has provided a simple API to achieve this. All you need to do is using this TFLite converter, you can easily specify an optimization policy and convert your TensorFlow model. You will end up with the TFLite model that is usually 4 times smaller and 1 to 4 times faster. Note that some ops are not supported by the TFLite right now. So if you know some of the ops that you're using is not supported, you need to enable this to skip those unsupported ops. You can also do this by design. If you know some specific layers, you want to keep its accuracy because it's important for prediction accuracy. Note that the final TFLite model will be slightly larger than if you can quantize all the layers. A few tips and tricks that we learned throughout this process is first, debugging conversion can be tricky. It's just because it doesn't directly give you a very clear message on which layer is failing. So, but the practice that we found is helpful is that you add the layer by layer and try to convert and see where it will fail. Secondly, if a specific layer fail, there is usually some equivalent offset you can potentially use that is supported by TensorFlow Lite. So definitely try that before giving it up. The third is TensorFlow Lite is not optimized for the backend server. So the best way to test it is really directly run it on edge devices. That brings us to a tool that our colleague at SAP Concur has developed called Tiffin. This is what we use to benchmark all our models before deploying actually to the mobile. This tool allows you to upload your model, upload your test set, and then it will run based on AWS device farms to get a realistic estimate on the memory and inference time on all kinds of mobile devices, including iOS and Android. Here is a link to it if you want to learn more about it. That concludes the main part of our presentation. The key takeaway is when you are designing or deploying a model, keep in mind your target deployment the environment. Because if you only drive on accuracy, sometimes it will end up with a model with much high complexity, which has a bigger size and latency, and then it makes it hard to deploy on mobile. Also, you might use some specific ops that are not included in, for example, TensorFlow Lite, that might end up a slower and more resources expensive model that might be difficult to deploy to edge devices. We cover some methods to make your training and deployment mobile friendly, including using TF functions, using quantization aware training, and sharing architectures between models. One last recommendation we've made is test your conversion and benchmark performance early and often, just as you would do with your model accuracy, because when you are trying to deploy your models to mobile devices, this becomes as important as your accuracy. So that concludes our talk. It's time for Q&A, but I don't see any questions in the Q&A yet. So if you have any questions, feel free to submit them. Thank you. Crystal, hi Crystal. Ask questions. Are you familiar with any pre-trained models in the medical field that can be adapted for different use cases? Also, are there risks and benefits associated with pre-trained model versus one built from scratch in this instance? Ivana, do you want to take it?
Yeah, sure. So yeah, that's a very good question and a very interesting one. So I think it will really depend on your use case. For us, for example, both having a pre-trained model means that you're putting in a lot of additional layers that you might not need for your specific use case. So that could result in unnecessarily too big of a model to put on a device. So it really depends. Like if you don't have limitations such strict as the mobile edge device, then definitely go from a pre-trained model. There are certain benefits of that, certainly like a more efficient training, faster, etc. And still with fine-tuning, there are customizations that you can make for your own usage. However, like with constraints on mobile, depending on your model, it would either be using pre-trained models, but then using that like distilled training to make this big model into a smaller model and then convert it to TFLite, or I would recommend training from scratch with the model size that you would need. I hope that answers the question.
Yeah, just to comment on that as well. I think there's like mobile nets, etc., that are pre-trained like image-based models that can like very mobile deploy friendly. But again, it goes back to if it actually worked with your use case. But I would think that's definitely a viable route to try and see. And Jimmy has a question of, since many of us have mobile devices and might want to try this, what device do you have for learning and trying out models?
So
What
I would,
device? So, oh, go ahead, Ivana.
oh, I would just recommend doing a simple tutorial. There are a bunch of, and I'm happy to share the links later on if you contact us over Excel events. But there are certain tutorials where you could, for example, build a very simple image classifier and then try to put it on an Android or iPhone device. So it will basically teach you everything from like training this to become a TFLite model to how to build a really simple like mobile app. So I'm happy to share those links with you.
Awesome. Tucci has a question. Have you tried working with lower bit CNNs like 4 or 2-bit quantization? And is it hard to implement and better to stick with 8-bit?
So yeah, that's a good question. So we haven't really experimented much with that. We were kind of like going with the safe route of 8-bit and just being sure that we don't lose too much of an accuracy there. So, and we gotta like, it's mostly you go as low as you can and then you get a green light from like the mobile team that is implementing this, that the size and latency are okay. But definitely, yeah, we could going forward be experimenting with these.
Yeah, I think it's definitely worth trying. I don't know if it's hard to implement because TensorFlow, what it really offers is 8-bit. I actually didn't know how to, if we need to customize it to do it.
Yeah. I think there are stricter optimizations that you can apply, but I think depending on your use case, it might cost you a lot of accuracy loss there.
Cool. That's all the questions we have, and I think it's time. And that concludes our session. Thank you all for coming.